Good morning, everybody online.
Morning, Sam. How are you?
You're getting cold outside.
Yeah, I saw the clouds coming in with that cold wind last night when I took my dog for a walk. And I thought for sure we were going to wake up with snow on the ground. But it's just not a snow-filled year.
Hey, Mackenzie, can you mark my attendance?
Sure, Kyle. Sure. Sure. Yep, absolutely. Thank you. Yeah, it just, I couldn't see it at all. Okay. That's correct.
You can see them in the
That's correct.
area.
Okay, those are all correct, Sam. I'll put your points back.
No,
I just could not read it from the scan. The top of the page like was distorted when it uploaded.
It's kind of weird, like, I have a really big bunker that's right in my face. Usually unless it's blurry, it's pretty good.
Let me put those points in for you real quick before I forget.
All right, thank you.
Did you have a question, Joe?
No, ma'am.
Okay.
Well, I guess so. What are your office hours today?
Today, it's either from 1 to 3 or 2 to 3. Let me look. My last class is. Hey, Caden. 2 to 3. I have a student coming for a tour at 3. Yeah, so 2 to 3.
You get your calculator good now?
No, this is the one I think that, we had to buy that one for physics. Radiation.
Oh, I got
And I had already had it. Radiation.
You recommend a
Just had a
certain
picture
brand?
of the one that he was wanting to use. I think that's it.
Me?
No, Clausen recommended a certain brand. of
I hate that
something.
criteria.
It's hard to.
Caden, do you want me to do your attendance?
Yes,
The
please.
one thing I like is that, and I don't know if I just was playing with it yesterday at the store,
Yeah,
It'd be
and
nice.
then you call.
yeah, I like that feature too.
I like the one
I
on
think they
Hill.
have it on this. No. Right here. So. And then we call it,
That's the same that we use with Sherry.
right here, REC.
We call, oh, okay, the same thing.
But I should bring it. So many dang calculators.
Did you mark me
I don't
present
know
or
on my
something?
other calculator, I can't get it to
Did I?
go out enough.
I didn't mean to.
don't
I might
know.
have-
Oh, really?
When I touched the screen, I might have touched yours because you're next to Sam on my screen.
I'll get another calculator. I don't know why it isn't, it does at times, and it doesn't at other times.
Okay. Just real quick, there were on the K-effective calculation questions, a couple people, I took a few points off for not consistently having 4 digits in your answers. So just make sure across all your answers, you're carrying out to 4 digits. And if the digits are zeros, still write that down so I know that you went out to the right number of digits. Okay, so I was pretty mild on the grading. I just took a couple points off to remind you guys, but make sure that's consistent through this class on all your assignments, okay? Before we jump in to our next topic, does anyone have any questions on the homework we did or the lecture topics we've been going over the last week? Yeah, Sam.
Have you been posting the class recordings on YouTube?
Yes, I have. I'm typically posting all of the week's recordings that weekend because it still won't let me live stream. I just got them up Sunday for last week. Yeah, Joe.
Is a homogeneous reactor a synonym for infinite?
No. Homogeneous reactor means that there are not distinct areas where there is moderator, reflector, poison, and fuel. It's essentially if you took all those materials and made a slurry and then formed a cylinder of that. That would
Is
be,
that just theoretical?
yes.
Okay. All right.
Any questions on the Tucker reading? Are you guys enjoying that book? Did everyone like the explanation he had in there for K effective after we went through it in class? Was that some helpful reading to hear his wording? Caden at least thinks so. Okay. We're going to talk about subcritical multiplication. And tomorrow, we're going to introduce the 1 over m plot. On Wednesday, we're going to work on creating a 1 over m plot. And on Thursday, we're actually going to go down to the ISU reactor lab. They have a subcritical assembly with 19.9% enriched fuel that we're going to slowly put into a tank and do a 1 over m plot and calculate when that subcritical assembly would go critical, just like you would do for a reactor. So Thursday, you need to be present. If you've got a COVID reason that you can't be in class, I can have you do a different 1 over m plot, but unless you have a COVID reason, you really need to be at that lab. This was a big thing I noticed the last time I taught this class. We went over 1 over m plots theoretically a bunch of times, and I still don't think the students understood it that well. And so this lab, I think, is going to be extremely valuable. So I won't have Zoom going. Please be there. Joe.
Speaking of COVID, have you, the news did a story that there's been a sizable increase at ISU, including at the tech college?
Yes.
Do you know any of the details about the tech college increase?
I haven't. I know that last semester, the biggest area of concern was the hair program. What's the word I'm looking for? Cosmetology. Thank you. But I haven't heard any details on that. I know that with the screening program, they were hoping to not have people come back from break and be carrying COVID and be unaware. And since they had such difficulties with the screening program, I don't know if that was some of the issue, just that more people came back asymptomatic. And so then there's been a bit of a breakout because people didn't know, which is what I'm guessing. I haven't heard anything. But I have also not heard anything saying we need to be preparing to go all online either. So as far as I'm aware, we're still fine to meet in person and plan our labs and keep moving forward.
Is what we're doing on Thursday, is that gonna run over?
It shouldn't.
Because I have a class immediately after.
It should not run over.
And it's gonna be down on Lower Campus.
Yes. So do you guys all know where the Lily Bridge engineering building is? I know most of us took a tour there. So if you go in this door that's closest on the side from the traffic light, go immediately down the stairs. The reactor is that first door on your left downstairs. And we'll be in one of the, not in the reactor, but in one of the labs in the reactor lab area. If it runs over, Jen, and you need to go to your class, go ahead and go. Get the data from your other student teammates, and that will be fine. I have told Jonathan it can't run over.
My class is right next to
Down there. Yeah. If you need to go to your next class, go ahead and go. I told him it's just a 1 hour. He thinks we can do it. If it does start running over, because I know sometimes we've had not great luck going to other departments for 8 a.m. labs. So if something like that happens, you can get the data from someone else who can stay, and it'll be fine. Any other questions? Anybody online have a question? Sam?
Instead of these 1 m plots, you're going to be using reactivity, showing reactivity, or
So 1 over m plots are going to show multiplication as you approach criticality. And we're gonna explain that right now. Can you guys see that presentation online?
Yep.
Okay, great. All right, so we're going to start with defining 1 over m, well, subcritical multiplication. We're going to talk about our 1 over m formula. And then we're going to talk about some of the applications of this in reactor operations. When a reactor is shut down, neutrons are still present to interact with the fuel. So even when we fully insert our control rods, we don't 100% remove all of the neutrons going through their neutron life cycle and creating fissions. There is still some small amount of neutron multiplication that is occurring even in a fully shut down reactor. It's occurring less and less each generation because we're shut down, right? We're not increasing in power, but it is still occurring, and it would take a very, very long time of being shut down for it to stop. Have you guys all heard of the Oklo natural reactor in Africa?
Yes.
Okay, so even still, now, millions of years after it stopped reacting, you can still count subcritical multiplications happening in the Earth's surface at Oklo. As long as neutrons and fissionable material are present in the reactor, fission will take place. We have enough fissile mass in the presence of in the form of our fuel to create fission. So even when we have a fully poisoned core, let's say it's a pressurized water reactor, and we put in all of our control rod, and we put in all of our boric acid, and we're trying to kill that fission reaction as much as possible, we can't do it perfectly. There's still some fission. So a reactor will always be producing a small amount of fissions, and that is what we call subcritical multiplication. Because the reactor is shut down, neutrons introduced to the reactor by this subcritical multiplication will have a decreasing effect on each subsequent generation, right? We are at a K less than 1 and a rho less than 0. We're going to have less and less neutrons in each generation when we're experiencing subcritical multiplication. Any questions on what subcritical multiplication is?
Does it ever stop?
After you have decayed away all of your fissile material. So after 7 half-life of uranium, which is several million years.
So pretty much no.
For terms of our operational experience, pretty much no. Joe, did you have a question?
So neutrons are introduced in the reactor. How are they introduced? Just by the previous fissions? But they have less of effect each time they go around? Is that what that means?
Yes. When we want to start up a reactor, because these fissions are occurring at a very low rate, we are actually going to put something called a neutron startup source into our reactor that will provide enough fissions to create, or provide enough neutrons to create enough fissions that our instruments can detect this. In a shutdown reactor, this is happening at such a low level, our instruments don't detect it because our instruments are calibrated to detect fission at full power, right? So that we can get information on our power trends. So we'll introduce a startup source so that we can read what's happening. So you don't start increasing your K effective in your reactor period and end up with a runaway reactor before your instruments can even tell you what's happening. That's the big danger with startup, is that your instrumentation can't tell you what's happening in the reactor unless you provide an outside source of neutrons. When we start approaching power from a shutdown condition, we're going to start increasing our subcritical multiplication. There's going to be an addition of neutrons. We want to go slow enough that we don't immediately become critical, what we would call prompt critical. we want just a little bit more subcritical multiplication. So this is where it's going to seem a little weird, because we're going to take our subcritical multiplication and we're going to be increasing it towards 1, towards critical, but the whole time we're increasing subcritical multiplication, we're still in subcritical multiplication. We haven't become critical yet. Does that make sense? Okay. All right. For a given value of K effective, there is an M value, which is the symbol for subcritical multiplication, that relates the source level to the steady state neutron level of the core. So what that's saying is, when you put that external neutron source into the reactor and you start moving towards a K of 1, there is an M that essentially relates how much came in from the source and how much we've increased our neutrons compared to how many neutrons there should be when the reactor is critical. So we're comparing subcritical to critical so that we know how many neutrons we have to add to our cycle to get critical. We translate how many neutrons we need to add to our cycle into inches of control rod withdrawn, or what you will do on Thursday, number of fuel assemblies added. So we take our neutrons and we create a representation that says, okay, I have a giant tub of fuel that I want to turn into a reactor. I put 1 fuel rod or plate, as we'll do Thursday, into the tub. I have this many neutrons. I should have this many neutrons at critical. If 1 plate is this many and I need this many, how many plates can I put in? Then you'll put in a second plate and say, okay, now 2 plates give me Y neutrons, but I still need D neutrons to get critical. How many plates can I go up? Then you'll add a third one. You're like, okay, now I have Z neutrons, but I need to get to D. How many more plates can I put in? So you're going to relate the number of neutrons that each fuel plate or each inch of rod withdrawal relates to how many you need to actually enter critical. Any questions on that? Okay. If we know the value of K, we can calculate our multiplication factor as 1 over 1 minus K. Most of the time, we're trying to get to a K of 1. And so this equation is not very helpful to us, right? But whenever we have a subcritical K, we can determine our multiplication, right? So this is useful if you work with a fuel storage facility, a fissile material storage locker. Those of you who want to work at materials and fuels complex and not work with the reactor, but work with some of the experiments that come out of the reactor, this multiplication formula will be a lot of what you use to ensure that you're not storing enough fuel in an area to create a reactor where you don't want a reactor. And most of the time, this K effective, regulatory requirements are that it's at most 0.95. Most places drop it down far below that. The fuel storage pit at the reactor in Missouri that I worked at had to be at 0.9, which is somewhat high. This is university, wasn't a very big amount of fuel anyway. When I was at the PWR in Louisiana, I think that their fuel storage area was kept at 0.85 or 0.875. So an even smaller number in their fuel pool. In a subcritical reactor, the one that's shut down, our neutron level in is going to be related to the source strength of the neutron source that we put in and our subcritical multiplication, right? This is very similar in expression to talking about K effective, right? We would multiply our number of neutrons times our K effective, right? To get the next generation. Here, to get our generation of neutrons, we multiply the source we're adding times the multiplication that's occurring. And that's going to tell us now how many neutrons we put into our core. So if that source is a certain amount of fuel plates, if it's a startup source, like a plutonium beryllium source that we put physically in the core during startup, this is going to tell us, based on how much subcritical multiplication is occurring and how many neutrons we put in, how many total neutrons we have. So if we have a subcritical reactor, K effective is 0.6, what is the subcritical multiplication of this reactor? What? 2.5. That is correct. It is on the next slide, but try to calculate it before you look.
That's the 1/1 minus.
Yes.
Can I ask a quick question just to clarify something?
Sure.
So the 1/1 minus K effective, that's what'll give you the multiplication factor that you use in the N equals S times M?
That is correct.
Okay, thanks.
So when we multiply the source and then some critical multiplication together, what exactly are we timesing this? So like what are we multiplying there? So like the source, is that the neutrons?
Yes, it will be some neutron source, whether that's because I've removed so much fuel poison and I know the reactivity of that, I know how many neutrons have been added, or I'm adding a physical startup source that has its strength of neutrons written on it in its specifications, or it's that I'm adding fuel plates that contain a certain amount of fissile material. It can vary depending on how you're getting critical, right?
Is that like a K effective, like on the source?
No, it will be a number of neutrons.
Okay.
And then that N that we're getting, this is essentially our N0 generation when we're talking about our neutron life cycle. Kyle.
There's multiple plates, or multiple sources, you just have multiple.
Yes.
Or is that not?
Nope. No, you would add them together if you're doing that. And then if you're making a change after a cycle, you just calculate the cycle again. Joe.
So if you have X amount of neutrons, like 1,000, and you multiply them by this 2.5, that's how many neutrons you would need to get to K effective 1?
Not quite, because your K is 0.6. With that subcritical multiplication of 2.5, you're going to get that many more neutrons at that K. And then you would extrapolate how many neutrons you need to get to a K of 1.
Are there units on any of these?
For K effective, it'd be delta K over K. For subcritical multiplication, it can depend. It can either be in terms of neutrons, so just a number, or it can be an amount of reactivity. It can be a number of fuel plates, because you're going to be representing whatever you're adding to get towards critical.
What was delta K over K?
That's a unit of K effective.
Oh, yeah.
Did anyone not get 2.5? Everyone understand this? It's really straightforward, right? Okay. What if we have a K effective that's almost 1?
always gonna be in a 2 and a 5?
No, I just picked a calculation that worked out that way. What'd you say? So as we go from just above 0.5, about half of our K effective, to almost a K of 1, is our reactor about to get critical faster? A lot faster, right? This is one of the difficulties in operating and why startups are one of the more likely times you are to run into an issue with controlling the reactor. Low power operation is another area you're likely to run into issues with the reactor, and was in fact the issue that led to Chernobyl. They were trying to do a low power operation. The closer you get to K effective, the more your reactor wants to be critical, and the faster it's going to try to get to critical, which means the easier it is to jump to supercritical. Okay. We talked about the fact that we have trouble detecting our neutron multiplication when we're starting up a reactor. Power in a reactor is proportional to the number of neutrons present in the fuel material. Have you guys all seen the symbol for proportional? The light. So this squiggly, is that what you're talking about, Lynette? Okay, because that squiggle is approximately equal. This is an almost infinity symbol, is what it looks like on the computer. And this means proportional. So the number of neutrons is proportional to our power level, which is why we can have nuclear instrumentation that counts neutrons, but gives us units of power on our reactor console. The power produced by a subcritical core will be proportional to the subcritical multiplication factor plus any external source. So when the neutrons in our subcritical core are too low to be detected by our neutron instruments, we can add an external source during startup and low power so that we can measure our approach to criticality. And we're going to talk about tomorrow how we measure that with a 1/m plot. That's the way we start measuring our approach to criticality using subcritical multiplication. I have a different presentation where I talk a little bit about some of the different types of sources that we use. A lot of times they are a piece of highly enriched or fissile material, something you normally don't see as a fuel source, that produces a lot of neutrons in a very small package. The startup source at the AGN reactor on campus is about the size of a button source stuck on the end of a metal pole so that we can push it all the way into the reactor. So they're small, but they produce a lot of neutrons. In addition to needing to understand this for startup detection, it can actually be exploited for a number of different applications. We know the critical mass of different shapes and materials because the Manhattan Project measured subcritical multiplication in a bunch of different configurations using the 1/m plot that we're going to learn the rest of this week. And they tabulated what the critical mass will be. And then they had a couple of accidents that actually gave them a lot of detail about how close they rarely were to getting critical. Very unfortunate accidents, but they took that data and really confirmed they were on the right track. That was how they picked the mass that went into nuclear weapons. Today, these measurements and this technique is still used to design our fuel storage pools, our fresh fuel storage racks, all of the experiment material storage lockers at facilities like MFC that have various investigation objects that are not just standard fuel. It's how we design transport casks to not be mini reactors, right? We can transport fuel, and it's not a reactor because it's not enough material to go fissile, go critical together. And we know how much material that is because we can take the cask and we can measure how much fuel would fit in that shape to be critical, and then we can design it physically so that much fuel can't be put in it, right? So this technique of 1/m is also one of the bases for our safety calculations whenever we're storing fissile material. Subcritical assemblies, like the one that you will measure with on Thursday, can serve as a steady source of heat generation. So even though you're not going to get as much heat as a critical reactor, we still have fissions happening, as demonstrated by the fact that we can measure our subcritical multiplication, right? Every fission creates heat, right? And so where there's an application where you don't want a critical assembly, you can use subcritical assemblies to generate a small amount of heat. These are often called pickle barrel reactors. That subcritical assembly you're going to see on Thursday, that's kind of the affectionate nickname. And you can use them for training like we're going to. They can also be used to test materials that you want to store safely. And you can also do research on improving your instrument's ability to detect and discriminate low intensity multiplication. Our ability to detect down in the subcritical range has improved dramatically. And it's why we can have detectors in storage areas that will warn us if our storage is starting to reach an unsafe condition. We're starting to get a criticality there. We can detect much lower amounts than we used to be able to. Any questions? Any questions online? Okay. So we're going to focus on this startup plot. We're going to go through a couple examples today and tomorrow in class. I'll show you how to do it tomorrow, and then I'll give you some values, and we're going to create a plot in class on Wednesday, and then you're going to collect the data Thursday to create a plot, and that plot of the subcritical assembly is what's due on the assignment. You can plot these by hand if you have engineering paper or graph paper and you're a neat person. If you prefer to use a graphing or plotting application on your computer like Excel or Google Sheets, I would make sure that you have that with you on Wednesday and Thursday to get the data. I will accept either form, handwritten or computer generated. Okay. On Wednesday here in the classroom, we're going to create a 1/m plot together with some data I've just generated, I've picked. Then we'll go collect data from an actual subcritical assembly on Thursday. When I taught this class last year, we did both plots with just data I had generated, and I felt like it didn't give the whole picture. And also, you're going to get to go handle some fuel and put it in a tub, and that's kind of cool. So, put it in a pickle barrel reactor. Okay. Any questions on what we covered? I actually went through that faster than I expected. but I don't want to jump ahead too much. So I'll just introduce this equation we're going to use for our 1 over m plots, and then we will save the rest for tomorrow. Okay. It is a regulatory requirement that you should monitor the neutron activity in a reactor at all times, even when shut down. Okay? As we stated, our instruments are designed for full power. So what's going to happen is that your nuclear instruments are going to have scales. And there's going to be a scale just like on your frisking meters, right? The times 1, times 10, times 100, times 1,000 when you're counting neutrons. You guys all remember that scale setting on our detectors? Same thing exists for our nuclear instruments on our control console. When you're in your lowest scale, with a startup source, you can read those shutdown levels of neutron. And then as you go up in scale, you'll start multiplying by, instead of 1, 0.1, 0.01, 0.001. And that allows you to read all the way up to full power. The biggest error I made as an operator was forgetting when to change scale and repetitively scramming a reactor because it thought it was producing way too many neutrons, when in actuality, my instrument was just reading on the wrong scale, right? So as you go up in power, usually there's a rod interlock where you cannot increase in power anymore at maybe 75% of your scale. And then there's going to be an automatic rod insertion at like 80%. And then at like 90% of your scale, there's a scram. And so if you keep going up in power without switching up to the correct scale, your reactor thinks you've just exceeded 90% of your limit when really you're 3 scales down and you're fine. So be aware, switching scale is something you have to be prepared to do as you do a startup and go up in power. Small movements of control devices can result in large rates of change, especially at low power levels. We just saw that going from 0.6 to 0.996 K effective went from 2.5 multiplication factor to a 250 multiplication factor, right? So as you go from very shut down, right, our shutdown levels might be 0.5, 0.6 to almost critical. The closer you get to critical, the faster your reactor is going to want to approach critical. The more likely it is for this to jump up on your scale and up on your reactor period. So that's what we use a neutron source for. Sources are typically going to use the gamma rays provided by your fission products, and they're going to create a neutron. This particular one is called a photoneutron source, and it uses deuterium, and it produces a neutron and hydrogen. This is a very common type of subcritical source. This is what I have used before. It's called a plutonium beryllium source. You have plutonium and helium and uranium. So your plutonium is going to alpha decay, right? You get uranium. That alpha is going to interact with the beryllium that's on your source. So it's a little plug of plutonium and a little plug of beryllium on a stick that you can put in the reactor. When that alpha decay interacts with beryllium, you produce carbon and a neutron. Because we're trying to produce neutrons in our sources, right? We want a very reliable way to do that. Plutonium beryllium sources are nice because the plutonium lasts for a very, very long time. So when you buy this source, you can produce neutrons for a very long time. Beryllium, though, can be toxic. There's a toxicity factor for workers. So they're usually doubly encapsulated in steel. And that means that there's really poor heat transfer. So if you forget to remove your source when you reach critical, you can start to have an issue with maybe melting this encapsulated source, and then you have fission product release that we don't want, right? So it's very important that you are aware of your procedures when you put this in and when you take it out. Plutonium beryllium sources could be made by mixing plutonium and beryllium metal powder together, or surrounding a solid plutonium rod with beryllium. Which do you think we would want to use?
A rod.
Why the rod?
Wouldn't it be hard to mix?
We don't want the canned powders, do you?
Don't want decaying powers. Okay.
Wouldn't
It's
the
your
powder
control.
Sorry, say that a little louder, Haley.
It's your control. You put them in the rods so that you can control it.
Okay. What were you saying, Joe?
Wouldn't it be hard to mix the powder in the right proportion? Or dicey or risky?
Maybe. Could you what? We would ideally not like plutonium in our water, in the coolant. We don't want particles in general in our coolant. So there is a safety reason that powders are unattractive. What type of radiation are we dealing with?
You don't want dust.
How far does alpha travel? So if you have two rods, will the alpha go all the way through the plutonium rod to regularly interact with the beryllium rod? Not with good efficiency. So you actually only use the powders so that that alpha can actually leave the plutonium granule and be able to travel far enough to hit the beryllium granule. So this is another reason it's double encapsulated, is that we're dealing with powdered sources, of the powdered form of the materials, so that we can actually get enough efficiency to produce enough neutrons that we don't have to have a significant amount of plutonium.
So the powder's in the rod, is what you're saying?
Yes, they mix the powders together, they put it in a little double encapsulated plug, and then they weld that to the end of a metal pole, and you put the whole pole in to the reactor as your startup source.
Okay, well, your question was a little tricky.
It was, Joe.
I was reading about that site in Amarillo, Texas,
Yes.
and they were saying something like that, where they're dealing with alphas, which are not that dangerous unless you inhale them. They were saying that there's that risk at that plant. What are they doing? They're messing with powders like that?
Yes. And also a lot of times when we have a metal that is releasing alphas, especially if it is Manhattan Project era, it has often degraded. And you know how not necessarily when you see rusted metal, but when you have old brittle metal, sometimes you might move a sheet of it and it just crumbles. A lot of times that's what we're dealing with, some of these that have oxidized, that have had a lot of strain, a lot of heat through them. And so when they're disassembling various Manhattan Project era items, you're creating this metal dust because the metal just fragments so much, so friable.
So they're not doing it on purpose, but they have the same problem because the atoms are using it the same.
Yes, and then of course, there are facilities that produce these, right? There's facilities that manufacture these. And so they have a huge alpha issue. And so usually what they do is they use a glove box. And then they put a filtration system on it and a atmospheric control system so that dust never leaves the glove box and you never put your breather inside the glove box. So you can't inhale the alphas. That's the most common radiation source you're trying to protect against when you use a glove box with an atmospheric containment system. Okay. These are our generations of subcritical multiplication. They're not our generations once we're critical, right? So we talked about neutron generations. They're going through the same form, but you're not going to have criticality yet. So we're increasing, but we're not yet critical. So this is where it's very important that you realize you're either talking about subcritical multiplication or a critical reactor that's moving towards supercritical, okay? If your source, say it's plutonium, beryllium, that you put in has 100 neutrons, and your multiplication factor is 0, you're going to stay at 100 neutrons, right? If your multiplication is 60, you're going to jump up to 160 neutrons in that generation 1, right? As we continue to add more neutrons to each generation through our multiplication, we get more and more neutrons. Here at the end, we have the same value because as we added that one more neutron and then tried to go up again, we didn't get any more off the source. Now we're critical. Now we're going to start getting effective multiplication rather than subcritical multiplication. And our reactor is going to be running on its own neutrons. And if we remove the source, it won't affect anything because there's enough neutrons in the fuel that that reactor will be able to sustain its own reaction.
So that's N one.
This would be subcritical in 10 or critical in 1.
Right, yeah.
Multiplication is going to increase and it's going to move very slowly as we approach critical because we're only slowly allowing more material to go in. Our number of neutrons is going to eventually reach a constant number, which means we're then critical, right? At that cusp of changing from subcritical to critical is where we have a risk of jumping to supercritical because we want to not make many changes as we get critical, but we're still adding fuel or removing poisons, right? And so if we're not doing this at a very slow rate, this is where we can suddenly jump to supercritical. Do you have a question, Joe? No? Okay. Essentially, you're going to add a series of your subcritical K times your source neutrons. And this series eventually works out to this equation. Your source over 1 minus K. As you add up this essentially infinite series, we could write it in this form, so we don't have to add each time. We're going to rearrange this into the actual useful form that I want you to remember. 1 minus K over the source over counts. This is one term and this is one term. So this is the big division. Okay? When you plot this, we're going to call this inverse counts. And you're going to plot those inverse counts on the vertical axis. And the horizontal axis will be either your control rod position, your poison concentration. We do 1 over M plots to determine how much boric acid to add. to a pressurized water reactor are fuel loading. So on Thursday, the number of fuel plates that get added to the subcritical assembly, that's going to be your horizontal axis. The point where the plot crosses the horizontal axis is going to tell you where K equals 1. So what you'll do is you'll say, okay, I have this many counts, this much fuel. And then I have the next point of this many counts and this much fuel. And you're going to draw a line between those 2 points, all the way down until it crosses your horizontal axis. You're going to say, okay, based on these 2 pieces of fuel I put in and the counts I've measured, I say the reactor is going to go critical at this number of fuel plates, right where it crosses the vertical axis, or sorry, horizontal axis. Then you're going to put in another piece of fuel, and you're going to draw a line through the last 2 points. Because now you have more neutrons, your detection information is better. Where that line would extrapolate and cross is now where it's going to go critical. And when you actually start having the line, that point cross at the same place, now you have an accurate prediction. So I'm going to show you what one looks like real quick. Right? And so here you extrapolate until it crosses, right, at 8. But beforehand, when you got your first 2 data points that were maybe here and here, maybe it said 6, right? That slope is going to change as you get more and more data points. We're going to go into this on detail tomorrow. But are there any questions right now? Okay. We're going to go ahead and end there. Any questions online before I stop the Zoom? Okay. All right, we're done, guys. I will see you later.